a standard setup of algebraic geometry. So namely, I have ideals I in polynomial ring K of x1 up to xn, and over here I have subsets x in a n k. And the relationship, of course, is that I've got an element f in there and a point p in there, then I can do f of p is an element of k. So in other words, these things are not just polynomials, but they're polynomial functions of points in the affine space. And so I have these two correspondences. There's a thing that's called v that goes that way. So this sends I into v, let's say j, sends j into v of j, which is the set of points p in an such that f of p equals 0 for all f in I. And then the other way round, there's a correspondence called I, which is taking some set x there, and it's mapping it into I of x. Later on it will usually be called I sub x, which is the set, the ideal of f in k x1 up to xn, such that f of p equals 0 for all p in x. Okay, so when I started on the material of chapter 3, so there's various formal properties. And it's basically formal that if x is an algebraic set, in other words, if x is one of these v of j, then actually I can say it this way: x is an algebraic set if and only if v of I of x equals x. Right, so if x is an algebraic set, then there's some polynomials that vanish on it. So I take all of those, and then I take the set of all points where those guys vanish, and that's exactly x, no more, no less. Right, so this is assuming that x is already of the form v of j, then I get this. And then, so from this point onwards, we use the Nullstellensatz. So assume K is algebraically closed. Right? So you know, we must do this, or we can't really start doing algebraic geometry proper. Right? And so from this point onwards, so given I have that a given j, let's say, then I can do v of I, v of j, and then I can come back, right? And this is equal to j if and only if j is radical. So j is radical means that f to the n in j implies that f is in j. Okay, so this is just the Nullstellensatz. So in the last two lectures, I spent a lot of time proving the Nullstellensatz, and you remember there's all kinds of sort of finiteness conditions on rings, and so on. It goes in that, and you have to get it exactly right. But from that point onwards, basically you can forget the proof and just take it for granted. So the Nullstellensatz has already been proved. So I proved it last week, or it's proved in quite a number of different textbooks. And so we can sort of basically forget about worrying about the proof of the theorem and just use it. And so this says, and now if I say, I can take this correspondence and just make it into a bijection. So if I take radical ideals there, and I take algebraic subsets x in A and K. So let me say J in K of x1 up to xn. So okay, let me put curly brackets around these. So I mean the set of all radical ideals there, and the set of all. Then there's just a bijection. So there's V and there's I here, and they are bijections. Right, so this is a statement that you should remember. So in the middle of this we use that K is algebraically closed. So it's just not true if K is not algebraically closed, so you better be aware of that. But from this point onwards, knowing the algebraic set there is basically the same as knowing the ideal of all functions that vanish on it, and that's a radical ideal. And conversely, knowing an ideal is the same thing as knowing an algebraic subset. So, you know, this is sort of quite good. I mean, because here we have in mind that we can use the methods of arguing the tools, the ideas of commutative algebra. So, you know, in particular factorization, things like this. Ideas from algebra. On the right-hand side, we can use ideas from geometry. So in particular, you know, you might think, let's take K to be the complex numbers and use ideas here, for example, the ideas of topology or the ideas of complex analysis. So this is sort of a very rich setup. You have these objects called algebraic subsets, or called ideals of polynomial rings, and you can treat them by a whole variety of different tools. So I should give some examples, because otherwise you won't see what's going on. So on the other hand, you know, I don't want to do exactly the same example. So let me do this one. You remember you remember these equations. So u v maps to u cubed, u squared v, u v squared and v cubed. Right. So when I had this before, I was thinking of this as taking P1 and embedding it in P3 as the twisted cubic. So they're the same equations. Right, but I want to use it for a different purpose here. I want to use it just to give map from affine space there to well, this is in affine 4 space, right? And I'm mapping it to some surface. So S. So S is the variety, the image of phi given by right, and so we know, I mean, we already know the equations of S. We know the equations of S are, so let me call these x, y, z, t. Then we know the coordinates are, the equations are x, z equals y squared, and x, t equals y, z, and yt equals z squared. Or equivalently, we can write these as x, y, y, z, z, t and say rank of this matrix less than or equal to 1. So saying rank less than or equal to 1 means exactly that all the 2 by 2 minors vanish. Right? So when we did projective space, we were forbidden, we were not allowed to have all of these 4 guys 0, because that was one of the conditions for projective space. Here, they can all be 0 if they want to. So this rank is genuinely less than or equal to 1, and there is the point, this matrix can be 0, 0, 0, 0. Right? So, we had this before. This is now a surface in 4-dimensional space, and I'm saying you need 3 equations. So, what would happen if I take only 2 of these equations? So if I take, for example, if I take J to be, J1 to be xz minus y squared, and xt minus yz. So these are 2 equations vanishing there, and haven't we done enough to determine the variety? So exactly as before, you notice, just look at these equations and you say, aha. So if x and y are not both 0, then this says that z is y squared over x, and this one says that if they're not 0, this says t is yz over x is y cubed over x squared, and so the first 2 equations imply things like this, imply the 3rd equation, yt equals z squared. If not x equals y equals 0. If we're not on this plane. But anyway, so if I take the V of J1, you can see eventually that you get surface S union the plane x equals y equals 0. And so this is the ZT plane. So, that's just a sort of trivial little example involving no further computation. So, I want to pursue this example some more. I want to say let's take the section S intersect H, where H is x1 equals y equals z. Right. So I've got something which I'm sort of thinking of as a surface here, and then I'm saying let's cut him like this by a hyperplane H. Right. So I hope everybody can see what's happening. If I do this, then I had x, y, z, t, but z is just y, right? And then what do these? They're going to end up being the points. So this is the set of points lambda 0, 0, 0 and 0, 0, 0 lambda and lambda, 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 lambda. So this is the union of 3 lines. Right, and this is going to be defined by, so this is in space x, y, t, and defined by so with z equals y. I mean, that's just defined by these same equations. So x, y equals y squared, and xt equals y squared, and yt equals y squared. Right. So you know, if we were sort of drawing these geometrically in a plane, we'd sort of think of drawing. There are 3 points here, and I'm drawing something like so xy equals y squared is x minus y times y. So this is the line. So you know, I can think of this as L1, L2, L3. What? You know, I really want to draw these three lines, and so you know, in this case, starting from J. So let me call this J2. Starting from J2, we can find all the solutions as a parameterized set. Right, so I mean, this is just, you know, we use factorization and then, well, pretty trivial linear algebra. So if I want this to hold, then I have to have either, you know, at the end of this there's y times y minus t, and so I have to have either y is 0 or x equals y and y equals t. Right, so x equals y and y equals t is this line. So I'm thinking of sort of L1, L2, L3. So if the y is not 0, then these two guys are 0, which means I have to be on this line L2. Right? And then if y is 0, then we're going to have a choice there. If y is 0, I've got to have either x or t is 0, so I must be on this. So in other words, I can take the equations, I can sort of think about them, in this case factorize them, realize that product equals 0 means one of the two factors has to be 0, and then do some, you know, well, in this case it's absolutely trivial. The equations are saying I've got to be that point or that point or that point, but, you know, more generally we might have some linear algebra to do. But anyway, we're finding solutions as a parameterized set, and it's basically the same as first year linear algebra. Right, and given, so this, and given x, so let me call this x2 equals L1, L2, L3, we can find the ideal J2 by substituting. Right, so if I take polynomials in 3 variables and I say they've got to vanish on these 3 lines, then you know, eventually you can persuade yourself that they must be a polynomial. I can subtract off multiples of those 3 guys to get 0. So any f of xyz, xyt, sorry, that vanishes on L1, L2, L3 is a linear combination of the generators of J2. Right. So in this case, we're sort of going backwards and forwards between the two by explicit and rather easy calculations. So the Nullstellensatz says you can do this. You can do this for however complicated the algebraic set and the ideal R, the ideal J are. So I've got this X and this J, and they may be horribly complicated. There may be things where you can really not work explicitly at all, but nevertheless you can do this manipulation. So, you know, I mean, basically much more trivial example that we've already seen. So if I do, for example, something like this, if I do J is the ideal. If J is the ideal, you know, x squared plus y squared equals 1, and y equals 1, right, so I'm saying let's take the intersection of this curve, this just the ordinary circle, and this straight line given by y equals 1, then you can see very well that it's just the single point. V of j is a single point. Is a single point, so x equals 0, y equals 1, right? And then, and so if I do the ideal of v of j, then obviously I'm getting the ideal x comma y minus 1. So this element y minus 1 is just one of the original generators of j, but the other element x there, well, x squared, so x squared is in j, but x is not in j. Right, so this is exactly an example of this place where we really need to use the radical. Okay, so I mean, I'm just giving a very simple example to, you know, sort of underline what the theorem is saying. Okay, so what do I want to do next? So I'm going to remind you of this thing called the Zariski topology. On AN, K, and on X in AN, K. Right, so remember, here I say, given an ideal J, I go forwards to V of j in there, and this is an algebraic set. And these are the closed, the algebraic sets are the closed sets of a topology on AN. Right, and this is called the Zariski topology. Right, so you know, the word topology is sort of used, comes from analysis. There's this idea of, first of all, you do epsilon and delta calculus in one variable or in several variables. Then you do general metric spaces. Then you do general topological spaces. Right, but the idea that's happening here is really very, very different from that. Saying that they form a topology means, you know, the trivial things that the whole space and the empty set are closed sets. And then the idea that a finite union of closed sets. So if I've got a finite union of algebraic varieties, for example, I've got these three lines, that's still an algebraic variety because it's still a set defined by equations. Right, and then arbitrary intersection. Right, so these are just completely very, very formal properties, and they allow us to say this is a topology. So really we don't want to use this topology because we're doing analysis. We want to use it, I'll explain why we want to use it later. We want to use it really because we want to say what is the domain of definition. So the main use is the domain of definition of rational functions. Right, so quite soon I'm going to be discussing the functions on a variety, polynomial functions and the... okay, but at the moment I just want to talk about this, this basically VI setup, going from what are the set of algebraic sets and how they relate to the set of ideals. Right, so let me say, this is later. Right, so for the moment I want to say the Zariski topology on X. So if I've got an algebraic set here, then this is just the closed sets of Zariski topology on X are algebraic subsets. So let's say, some, V in X. So I've got X. X is now not the whole space. X is maybe a hypersurface or something that's much smaller. So it's some algebraic set in there. And then I say, right, the closed sets on X, closed sets of the Zariski topology on X, are going to be all algebraic subsets contained in X. Right? And, well, what do you have to say? So this is the same thing as the subset topology. This is the same thing as the subset topology of the Zariski topology on AN, but restricted down to X. Okay, so the very, very special thing about the Zariski topology is that in interesting cases, in most cases, it's irreducible. So we say that V is irreducible. So this is completely different from classical topology, from the Euclidean or the complex topology. V is irreducible means that V cannot be written V equals V1 union V2 with V1 V2 contained, strictly contained and not equal to V, algebraic sets. Right, so it's easy to give examples of things that are reducible, namely, if I take something like this, L1 union L, L2 union L3, then it's reducible. Right, and I proved at the end of last time that every algebraic set is a finite union of irreducible algebraic sets. So the idea is, here's my V, and I say, well, either V is irreducible itself, in which case it's the union of just one of these irreducible sets, right? Or V is V1 union V2, where these guys are strictly smaller algebraic sets. Right? And then I ask the same question about V1 and V2. So if V1 and V2 are irreducible, then we've won. Otherwise, I can decompose V1 and V2 again. And this process must stop. So the set of algebraic sets has the, so by Noetherian induction, this must stop, this process. With V equals union of VI, irreducible. Right, so you know, this is written formally in the book, and I went through the argument at the end of last time. The argument I said here about V1 dividing up into 2, and then, you know, each of the components dividing up into 2, and so on, is sort of just a little bit messy. And the algebraists have this nice way of saying, let's take the minimum example here and prove that it's not an example. So I'm not going to repeat that argument. Okay, I want to discuss this notion of irreducible because it's very important. So, irreducible. I said the definition here, it means that it's not like this. So, irreducible means that it has the following interpretation. Right, so so far I've said topology, but I've only said closed sets. So if you know the closed sets in a topology, then the open sets are just the complement of the closed sets. So what's an open set? So if I've got X, an algebraic set in AN, so it's always over some fixed field K, and the field K is always assumed algebraically closed at the moment, then an open set, a Zariski open set, well, by definition, is a complement X minus V, where this guy's Zariski closed. Right? So I told you I don't allow this. This is not an algebraic set, not necessarily an algebraic set. So it's not an algebraic set in ANK because it's defined by whatever equations define X. So there's the ideal of X. And then it's saying, and it's not in V. So this condition of being not in V is not a set of polynomial equalities. It's contradicting. It's saying that a set of algebraic equations does not hold. Right? So this thing, so NB, this is not, usually not, an algebraic set. Right? So what do I want to make of this? So irreducible is if and only if, so X is irreducible, if and only if any two non-empty open sets so let's say U1 in X and U2 in X. So this is not equal to empty. Have non-empty intersection. Okay, so you know, how do I prove this marvelous claim? I say it's completely trivial. Right? Because this is saying that U1 is X take away V1, where V1 is closed, and this is saying that U2 is X take away V2. And to say that if U1 and U2 are empty, it means that X, so if U1 is X minus V1, and U2 is X minus V2, then U1 intersect U2 equals empty means exactly that X is V1 union V2. Right? This is just tautology. This is trivial statement. I'm just taking the complement of the definition. The definition of irreducible is that this doesn't happen, and saying that it means this. Right? So irreducible is this thing, this property of algebraic varieties, meaning that it can't be split into smaller subvarieties like this, both of them closed algebraic sets. And, well, that's all very well. I'm the lecturer in algebraic geometry, so I'm allowed to make these kind of definitions. But this thing here is something which, probably you've never seen a topological space that has this property. Because if the ordinary topological spaces have this property. They're Hausdorff. I never know. Right? So if you take a metric, any metric space has this property. Any of the usual topological spaces that you're used to have this property. Right? So what is this? Let me explain what this property is really about. This property is really about the statement that if I... Let me try and... So if U in X is so let's say non-empty open set, and X is irreducible. Okay, so as I've got two functions, f and g, suppose these are both polynomials, x1 up to xn. The x is in AN. Then I say that if f restricted to u equals g restricted to u, this implies that f equals g. Okay, so I hope we can see that this is true. So I have this I have this open set. So because f minus g is still a polynomial function. So if this f minus g is 0 on u, so if u is not the whole of x, so sorry, if this if the variety of f minus g is not x, then it's a connected component. It's an irreducible component. Of x. Okay, so suppose I've got this, I'm in this setup where I have an irreducible variety. So I told you that every variety is a union of irreducible varieties, so there are lots and lots of irreducible varieties. And suppose in there I've got a non-empty open set. So this u is given by x, take away some smaller subvariety. Right, now I take this f and g, and I ask that f and g are equal when you restrict them to u. Right? And so this means I can take the variety of f minus g. And that's certainly a subvariety of x. Right? And it includes u. And u itself is the complement of some other subvariety. So if u is x minus v, then x is v union this variety of f minus g. This is a contradiction. I mean, it's a contradiction if this one is non-empty. It's a contradiction if this is not the whole of v. So v of f minus g is the whole of x. Right. So this is this property is like analytic continuation in complex analysis. It's saying I've got I've got two holomorphic functions. They're equal on some big open set, and then they have to be equal everywhere. So, you know, this is, I'm trying to make this plausible to you. I'm trying to explain. So this idea of irreducible we're going to see again and again, and we're going to use it often in this form. So this is kind of analytic continuation. Uniqueness of analytic continuation. Okay, so if you think about this property can also be expressed by saying that every non-empty open set, these are open, any non-empty open set is dense. So another way of saying, so irreducible if and only if I need to open non-empty opens intersect. So intersect meaning they have non-trivial intersection, and that's the same thing as saying any non-empty open set is dense. So in the Euclidean topology, here is a some area in space. Here's an open set. So U open in the Euclidean topology. So here is an algebraic variety V, and here is something which is open in the Zariski topology. So this is U open. Let's call this X in X. So U means that U is X minus V, where V is a locus where some polynomials vanish. Right? And so, it's perfectly okay to say that what happens when K is C. So a Zariski open, a Zariski closed set is closed. Right? It's closed for the simple reason that polynomials are continuous functions. Right? Because polynomials are continuous, so the set of place where polynomials are zero is a closed set, and this means a Zariski open is open in the complex topology. Is open in something which is open for the Zariski topology, like this one, is also open for the complex topology, but is also dense. Right, so it has all these points like this. It has near any point of the variety you can find one of the points in the open set. It has everything there except for where this little accident happens, and the accident happens, in some only along some subvariety. Okay, so this is an important notion and something that the Zariski topology is not very intuitive. You have to work to get used to it, and I'm giving you some of the hints. Okay, so I had AN K. I had the Zariski topology on AN K, and this corresponded to. So this has algebraic subsets, right? And these correspond one-to-one with ideals in the polynomial ring K x1 up to xn. So that's why I left that. That's why I left that box up. So what about the Zariski topology on? What about the Zariski topology on X? So it turns out here there is a ring. There is a ring K of X that contains this information. Okay, and so I told you the next thing, having sort of set up this general framework, this general Nullstellensatz framework, the next thing is we have to discuss what are the functions on X. And so far I've only used the functions in order to define algebraic subsets. I haven't really talked about the functions themselves. Okay, so this is basically going into the next section, or at least beginning to go into the next section. So I of X is the ideal of X. I mean, it's the whole ideal, the radical ideal. And then so define K of X to be X of x1 up to xn divided by Ix. Right, so if I've got f and g and so on in K of x1 up to xn, then they define functions. They define functions on an, right? And so I can take those functions and restrict them. So I can take f and I can restrict it to x. Right. Now it so happens if I take this, if I do this for two different functions, f restricted to x and g restricted to x, these are equal. Happens if and only if f minus g is in I of x. Right. And so this f minus g is 0 when I go down to this quotient ring. So f and g define the same element of K of x. Right. So if you're an algebraist, you have this ideal, and you take the big ring divided out by the ideal. You think of these elements here as being cosets. You think of them as being of the form f plus I of x. I don't want to think of cosets. I've never used cosets for any useful purpose in my life. Right. What I want to do is I want to think of the f, the class. So f in this K of x is the function. It's the polynomial function. Is the polynomial function f on ank restricted to x. Right. So by construction, this ring K of x, this is a on the one hand this is a ring. So you do this multiplication and so on. You can do the ring operations in it, right? But at the same time, the elements of the ring consist of functions on K of x, and moreover, these guys x1 and so on, xn. These are ones just the ordinary straight linear coordinates on the original affine space. These are functions on x. So this, the Nullstellensatz stuff, correspondence between ideals and subsets, algebraic subsets, continues for k of x and its algebraic subsets. Right. In other words, over there I was talking about the Zariski topology on X. So I've got X, an algebraic subset in AN, and the Zariski topology is the topology on X where the closed sets are smaller subvarieties. So now I'm going to tell you that the smaller subvarieties are controlled by ideals in this new ring in exactly the same way as here. And namely, so an ideal, let me say J in K of X. These guys correspond one-to-one to ideals, let's say J twiddles in K of x1 up to xn, such that I is contained in J twiddles. Right? So this is a quotient ring. If I've got some ideal in this quotient ring, if I've got some J in there, then the J certainly consists of elements that come from the big ring here, residues of elements of the big ring modulo this. So I take these guys and I lift them up. And I lift them up every possible way. And so I get this J twiddles. So you know, basically I'm just saying there is this ring K of X. Completely formally, it's defined by polynomial functions but restricted to X. And so this means that the an algebraic subset X, so V in X in AN. So I can think of it as V in X, right? But it's supposed to be an algebraic subset. So I told you the Zariski topology on X consists of algebraic subsets of AN that belong to X. So if I've got one of these guys, he's got an ideal. His ideal is J twiddles, and the ideal certainly contains I, because I is the set of all things that vanish on X. So the things that vanish on X also vanish on V. Right? So these correspond one-to-one with radical ideals J twiddles that contain I. Right. So anyway, so let me make a little digression now. The subject I'm talking about is sort of algebraic geometry before the introduction of schemes, and I've told you there is this notion of algebraic variety, and algebraic variety has this ring K of X associated with it. Right, so this is a ring, and it's of the form K of x1 up to xn divided out by some ideal x, where this is radical. Right, so there's some kind of correspondence here, so maybe I shouldn't draw an arrow. There's some kind of relation between these two objects. So what is the relation? So the relation is that I told you algebraic subsets of X correspond to ideals in K of X. So in particular, if I take a point in X, this corresponds to a maximal ideal MP in K of X. Right. So you know, I'm not saying anything non-trivial here. I'm saying something. I'm just introducing language. So you know, I had AN, and AN contains X, and X contains the point P. Right. So this point P is some point in AN, and so he corresponds to maximal ideal M, the capital MP, X1 minus A1. Xn minus An, where A1, where P is A1 up to An is contained in An. Right, and we had this part of the Nullstellensatz. This statement I said was the weak Nullstellensatz. If I've An, so you know, here I've got the polynomial ring K of X1 up to Xn, and the statement of the weak Nullstellensatz is that a maximal ideal of this guy here, a maximal ideal of this polynomial ring is of this form. So it's generated by X1 minus A1. So where this is A1 is the value of X1 when I evaluate it at the point P. Right? So if I want to get a maximal ideal here, I have to set all the xi's equal to some value in K. Right? Now this maximal ideal will belong to X if and only if this maximal ideal contains Ix. So P is in X if and only if this thing there. In other words, P is in X means that I take all the functions defining on X, all the functions that define X, and they're supposed to be contained in the functions that vanish at P. So all of this is just tautology. All of this is just you know, completely empty statements. But the conclusion is that conclusion. X is spec M of K of X. The set of maximal ideals of a ring. Right. So I could have said this at the time when I introduced this weak Nullstellensatz. I've got the ring K of X1 up to Xn. So, you know, he's an object of algebra. He's a polynomial ring in so many variables over a field K. I ask the algebraic question of what are his maximal ideals? Right? And the answer is his maximal ideals correspond one-to-one with points of a space. Right? And the set of maximal ideals of the polynomial ring here is called spec M, spec maximal. And it corresponds to these things. So you'll remember, of course, that prime ideals are radical. So prime ideals for P. Let me continue to call them J in K of X1 up to Xn. Right, and these correspond to irreducible algebraic sets. X in ANK. So this is still at the level of ANK. Right. So if I look at this K X1 up to Xn, right, then this is the set of prime ideals. So this is called spec of K of X1 up to Xn. This is the set of prime ideals. Right, so on the left-hand side here I have something which is clearly in algebra. I've got the polynomial ring. I've got the field K, I make polynomial ring X1 up to Xn, and then I ask for prime ideals in that. right? And then these correspond one-to-one with irreducible algebraic subsets inside this space, AN of K. And so in this case, I'm not going to talk about schemes to any degree, but some of you will eventually have to grapple with them. So, so spec of R is a set of prime ideals of ring R. And the thing we're seeing here is that this same Nullstellensatz says if my ring is K of x1 up to xn over a field, over an algebraically closed field, then its spec corresponds one-to-one with the irreducible algebraic sets in X. So you know, here's my variety X, right? And here are its points, right? And then inside there are also some high-dimensional varieties, some subvarieties that are not points. So if you're just being strictly geometric in a classical sense, you see the points and you say, right, I want to work with this spec maximal, right? But if you're, you know, the mathematicians of the 1950s and 60s, especially Alexander Grothendieck, then he says, well, let's also throw in these high-dimensional things. And so, you know, there's other cultural and historical and mathematical reasons for that. But anyway, this is called an affine scheme. I mean, it's a particular case. It's a case of. So the rings I'm working here contain a field and are finitely generated over a field and usually have no, usually integral domains or have no, you know, radical rings. So I'm not telling you the whole thing. Right? And then, so if I do spec of K of X, then the same game, the same words say that spec of K of X is a set of prime ideals of K of X. Right? And this is equal to the irreducible, a set of irreducible algebraic subsets of X. Okay, so I'm not going to think too much more about. I'm not going to say too much more about affine schemes or schemes in general. But some of you will, in the course of time, need them, and you know, it's sort of basically not very easy to learn about. But at least in this case of, you know, nice algebraic, the rings of classical algebraic geometry. What's going on here is really very simple and concrete, and you know, already the Nullstellensatz tells you most of what you want to know about it. So for the second lecture today, I'm going to talk about this ring here, and some other tricks we can do with it. So I think we're having a little organisational meeting here when Professor Lee arrives. So any problems with this material? I can try and answer questions if you